Every time an aircraft touches the sky, it carries more than just passengers. It carries a promise of uncompromising safety and engineering excellence. Behind every smooth takeoff and graceful landing lies a meticulous world of maintenance, governed by the philosophy: every flight, every day. Mechanics swarm the aircraft like a precision pit crew, unscrewing panels and beginning the rigorous inspections that define modern aviation reliability. To understand the scale, consider this. A typical long-haul jet circumnavigates the globe dozens of times each year, enduring extreme pressures and temperatures. Maintenance happens in layers. It begins with line maintenance, performed right at the gate between flights under the glow of a setting sun. Next is base maintenance, where planes enter the hangar for deeper checks. Engines are partially exposed, revealing the intricate clockwork of jet propulsion. The most intense is heavy maintenance, or the D-check. The aircraft is stripped to its skeleton, revealing the complex aluminum and composite frame. This cycle of care ensures that when a pilot performs their final walk-around, they are stepping into a machine refined to perfection. But perhaps the most stressed component of all is the landing gear, the unsung hero that manages the violent transition from sky to earth. At touchdown, 3 struts must suddenly support 300 tons. The impact creates a signature puff of blue smoke as rubber meets asphalt. The secret to surviving this force is the shock strut. It uses nitrogen and hydraulic fluid to compress 26 inches in a fraction of a second. Mechanical braces then snap into a locked over-center position, ensuring the gear cannot collapse under the immense weight of the moving vessel. The brakes are equally impressive. Made of carbon composites, they can glow red-hot during high-energy stops, absorbing energy equivalent to a speeding freight train. Once airborne, the gear must retract perfectly. Watch as this Boeing 777 gear rotates 95 degrees to fit into its narrow wing well. Aviation is a feat of engineering redundancy. Even if hydraulics fail, gravity free-fall systems ensure the gear always locks down before landing. From the smallest screw to the massive struts, every component is a testament to the rigorous standards that make flight the safest way to travel. Making aircraft components isn't manufacturing. It's alchemy. You start with raw metal and end with a part that must perform flawlessly in conditions that would destroy almost anything else. Let's follow the journey of a single landing gear component from raw material to flight-ready part. Stage 1. Material selection. Landing gear uses ultra-high-strength steel alloys like 300M or AirMat 100. These materials have tensile strengths over 300,000 pounds per square inch. The raw material arrives as forged billets weighing several tons. For comparison, mild steel is around 60,000 psi. Stage 2. Forging. The billet is heated to 2,000 degrees Fahrenheit and placed in a die. A hydraulic forge press applies 50,000 tons of pressure enough to shape the metal while aligning the grain structure for maximum strength. This isn't machining away material. This is forming the material into the optimal shape. Forging creates parts stronger than machined alternatives. Stage 3. Heat treatment. The forged part is heated and quenched in oil or polymer, then tempered. This process creates the exact hardness required. The part is tested for hardness at multiple points. Variation allowed, 3 points on the Rockwell C scale. That's incredibly precise. Stage 4. Machining. The forged, heat-treated part goes to CNC machines that remove material to exact dimensions. A landing gear strut might start as a 5,000-pound forging and end as a 2,000-pound finished part. 3,000 pounds of metal machined away. Tolerances are measured in thousandths of an inch. Stage 5. Surface treatment. The part is plated or coated for corrosion resistance against salt water and hydraulic fluid. Stage 6. Non-destructive testing. Before the part leaves the factory, it's inspected using magnetic particle inspection to reveal surface cracks. Ultrasonic testing finds internal defects, while eddy current testing detects subsurface cracks. If any defect is found, the part is rejected. Stage 7. Final inspection and certification. Every dimension is measured. Every surface is inspected. Documentation is completed. The part receives a traceability tag that follows it for its entire life, 30 years or more. Total time from raw material to finished part, 6 to 12 months. Total cost, $500,000 to $2 million. Every single part goes through this process to build something that absorbs 300 tons slamming into concrete at high speed, 150 miles per hour, again, and again, and again. A commercial aircraft has over 3 million fasteners. 3 million bolts, rivets, screws, nuts, and pins. And every single one is engineered, specified, and installed with surgical precision. Because if even one fails, the consequences can be catastrophic. Let's talk about aircraft bolts. They're not like the bolts at your hardware store. An aircraft bolt is made from high-strength materials, corrosion-resistant steel, titanium, or Inconel, a nickel-chromium alloy that withstands extreme temperatures. A typical aircraft bolt has several critical features. 1. Precision threading. The threads are rolled, not cut. Rolling creates stronger threads with better fatigue resistance. The tolerance is measured in microns. 2. Head markings. Every bolt head has markings indicating the material, strength grade, and manufacturer. A dash means standard steel. An asterisk means corrosion-resistant steel. A raised cross means AND standard. Mechanics can identify a bolt's specifications just by looking at the head. 3. Grip length. This is the unthreaded portion of the bolt. Too short, and the threads bear the load bad. Too long, and the bolt bottoms out also bad. Grip length tolerance, plus or minus 1/64 of an inch. 4. Torque specifications. Every bolt has a specific torque value. Too loose and vibration causes fatigue failure. Too tight, and you stretch the bolt, weakening it. Torque values range from 20 inch-pounds for small fasteners to over 2,000 foot-pounds for landing gear bolts. And installation isn't just tighten and go. It's a process. Step 1. Clean the hole. Any debris causes improper clamping. Step 2. Insert the bolt with proper orientation. Step 3. Add washers if specified. Step 4. Install the nut or locking mechanism. Step 5. Torque to specification using a calibrated torque wrench. Step 6. Safety wire or cotter pin to prevent loosening. Step 7. Inspect and document every single bolt. 3 million times. But bolts are just one type of fastener. There are also rivets, permanent fasteners installed by deformation. High-lock fasteners, combination bolt and collar with precise shear strength. Lock bolts, two-piece fasteners with permanent locking. Quick-release fasteners for panels that need regular access. Each type is chosen for specific reasons: strength, weight, vibration resistance, ease of removal, or cost. And here's the reality: modern aircraft are held together by fasteners that weigh less than a paperclip. Yet each one is responsible for structural integrity that keeps 300 people alive at 30,000 feet. That's not hardware. That's engineering. Landing gear and bolts are just the beginning. Aircraft are filled with mechanical systems that must work perfectly. Flight control actuators that move ailerons, elevators, and rudders against tremendous aerodynamic loads. Hydraulic systems operating at 5,000 psi, enough pressure to lift a building. Thrust reversers that redirect engine thrust to slow the aircraft on landing. Door mechanisms, cargo doors, passenger doors, access panels, all with multiple locking systems. Engine mounts that hold 60,000 pounds of thrust while absorbing vibration and thermal expansion. Every system is designed with redundancy. If one hydraulic system fails, another takes over. If one actuator jams, a backup system engages. If one bolt fails, the load transfers to adjacent fasteners. This is called fail-safe design. The aircraft can sustain damage and still fly safely. But mechanical systems don't just need to be strong. They need to be reliable. And reliability comes from testing. Before a landing gear design is certified, it undergoes drop testing, landing the gear from various heights to simulate hard landings. Fatigue testing, cycling the gear through 60,000 takeoff and landing cycles. That's 20 years of service compressed into months of testing. Corrosion testing, exposing components to salt spray for thousands of hours. Overload testing, applying 150% of maximum design load to verify structural margins. And that's just a landing gear. Every mechanical system undergoes similar testing. The result? Modern aircraft landing gear has a failure rate of less than 1 in 10 million flight cycles. Bolts and fasteners fail so rarely that failures are investigated as major safety events. This is mechanical engineering excellence, but the field is evolving. New technologies are transforming how we build and maintain aircraft. Additive manufacturing, 3D printing titanium and Inconel components with complex geometries impossible to machine. Smart fasteners with embedded sensors that detect loosening or fatigue in real time. Advanced materials like titanium aluminide and ceramic matrix composites that are lighter and stronger than traditional metals. Digital twins that simulate mechanical wear and predict maintenance needs before failures occur. The mechanical engineer of the future isn't just designing stronger parts. They're designing smarter parts. Parts that tell you when they need maintenance. Parts that adapt to changing loads. Parts that heal themselves. But the fundamentals remain: precision, reliability, safety. If this changed how you see aircraft mechanical systems, hit subscribe. Season 3 continues next week with more deep dives into aviation engineering. Drop a comment. What mechanical system surprised you most? Landing gear, fasteners, manufacturing? Let me know below. New episodes every Tuesday. Tap subscribe so you don't miss what's next. Thanks for watching, and I'll see you in the next one.